Have you ever wondered why some measurements are considered good enough, while others require what we call unmatched precision? In the world of chemical analysis, there is a distinct line between a general survey and a definitive measurement. Today, we're going back to the roots of mass spectrometry, the magnetic sector, the gold standard for isotopic ratio analysis. Think of a mass spectrometer like a high-speed racetrack. Before we can measure anything, we have to get our cars, the ions, moving. As we move into the physics of the bend, we'll see exactly how these ions are accelerated and redirected. As you can see on the slide, it all starts at the ion source. We use accelerating plates to kick these ions into a vacuum. Every ion enters the magnet with a certain amount of kinetic energy, determining its speed based on its mass. This formula is the foundation. EV represents the work done by the electrical field, which translates entirely into the kinetic energy of the ion. Lighter ions will travel faster than heavier ions if they carry the same charge and are subject to the same voltage. The magnet exerts a force that tries to pull the ion into a circle. At the same time, the ion's own momentum, its centrifugal force, tries to keep it flying straight. When these two are in a perfect tug-of-war, we get that distinct curve. If we keep h and v constant, the only thing that determines the radius r is the mass-to-charge ratio. This is the mathematical grace that allows us to separate atoms with such precision. The magnet acts like a massive prism for ions. Just like glass bends different wavelengths of light, the magnet bends different masses. We can scan the magnetic field to bring each mass into focus on our detector one by one. In a single focusing analyzer, we separate by momentum. But there's a problem. Not all ions come out of the source with the same speed. This velocity spread causes the peaks to blur, which is why the stuck practitioner often wonders why their resolution isn't higher. This is where we move from standard to high definition. Think of the ESA as a lens that sharpens the ion beam. It accounts for velocity differences so that the magnet can focus solely on mass. This is how we distinguish isotopes that are incredibly close in mass. So when should you reach for a magnetic sector instrument? If your goal is high reproducibility, especially for things like carbon dating, this is your machine. However, these are the grand pianos of the lab, large, expensive, and not suited for pulsed methods. Remember this one golden sentence. The simplest laws of physics still provide our deepest insights. You've just mastered the fundamentals of the most precise mass analyzer in history. Don't be intimidated by the scale. See it as a testament to our understanding of the atomic world. Give yourself a pat on the back. You've moved from an amateur to an expert who understands the roots. In our next module, we're going deeper into those electrostatic sectors to see exactly how they sharpen ion beams into surgical tools. I'll see you in the next lesson.